This is the part 2 video on force and motion. In the part 1 video, I looked at friction, balanced forces and unbalanced forces. Now in this one, I'm going to be looking at force and momentum. Please make sure to subscribe to the Physics Tips for Cambridge Students YouTube channel and hit the bell notification so that you get alerted of future videos. Without much further ado, let's get started. Now here I'm going to be looking at the IGCSE physics syllabus and looking at momentum in particular. All moving objects have momentum. A large truck moving fast has lots of momentum as compared to a slow moving car. Momentum is defined as follows. Momentum P equals the product of mass and velocity. Mass is given symbol m, velocity is symbol v, mass measured in kgs, velocity measured in meters per second. In symbol format, P equals mv. Now the units of momentum are kg meters per second, since we are multiplying kgs by meters per second. Momentum is a vector quantity, so we need to specify the directions. Now, momentum is a useful quantity in collisions and explosions. I'm going to be looking at collisions and explosions a little later in this video. Now, let's start off by looking at an example. Now, the example reads, calculate the momentum of a car of mass 1000 kgs moving at 20 meters per second. Now, the formula P equals mv. M is 1000 kgs, V is 20 meters per second. That gives you 20,000 kg meters per second. Newton's second law and momentum. In my part 1 video, I looked at momentum and I said that momentum, Newton's second law states that the resultant force is equal to mass times acceleration. Now, Newton's second law can be stated in terms of momentum as well. So F is the resultant force, and this is what I went through in the part 1 video, ma. But we know that acceleration is equal to final velocity minus initial velocity over the time taken. So instead of writing ma, we are now writing m. Then we substitute for a, which is v minus u over t, which comes to be, if I expand what's in the brackets there, it gives me mv minus mu over t. So we can say or conclude that force is equal to the change in momentum over the time taken. The resultant force acting on a body equals the rate of change of momentum of the body. So that's the expression for the second law of Newton. Resultant force acting on a body is equal to the rate of change of momentum of a body. Remember, in physics, when we say rate, we mean divided by time. So change of momentum divided by time is equal to the resultant force. So this is a more explicit form of Newton's second law. Now, multiplying by t both sides of the equation would give you Ft is equal to mv minus mu, and the quantity Ft is called the impulse of the force. If the force acts on an object for a longer time, the impulse is greater and the change in momentum increases. So what we are saying here is Ft is equal to mv minus mu. So on the left hand side, we have the impulse, and then on the right hand side, we have the change in momentum. So remember, impulse is the product of force and time, which is numerically equal to the change in momentum P. Let's look at this example there to reinforce this concept. A force acts on a trolley of mass 12 kg, changing its velocity from 4 meters per second to 6 meters per second in 3 seconds. Then says, find the force acting on the trolley using Fr is equal to mass times acceleration, and then also using Fr equals mv minus mu over t. Now, for the first one, we need to find the acceleration first. So the acceleration is equal to v minus u over t, and v is 6, u is 4, and t is 3. So 6 minus 4 over that will give you 0.67 meters per second squared. Then inputting it into the equation, F is equal to ma, we have 12 by 0.67, which then gives you 8 newtons. Then using Fr is equal to mv minus mu over t, we have to find the final momentum, which is going to be 12 by, so I'm going to change the color, so it's going to be 12 by 6 minus 12 by 4 divided by the time, which is 3. Right? So 72 minus 48 over 3, that's still going to give you the 8 newtons there. So whichever method you use, you still get the 8 newtons. Then the question goes on to say, find the impulse of the force. Now impulse is equal to, let me change that color again. So impulse is equal to force times time, which is going to be equal to the force 8 newtons times the time 3 seconds. That gives you 24 newton seconds. Then the question goes on to say, what is the force required to produce the same change in momentum if the time increases to 6 seconds? So from our equation, we said that impulse is equal to change in momentum. So here it says the same change in momentum, so which means that the impulse also hasn't changed. What has just changed is the time. So the impulse that we found is 24 newton seconds. So 24 newton seconds is our change in momentum, divided by the new time, which is 6. That gives us 4 newtons. So that is the new force. Then we are going to look at conservation of momentum. In collisions, the thing to note is that momentum is always conserved. That is, the sum of the total momentum is always conserved. Whether it is a collision or whether it is an explosion, the total momentum is always conserved. So consider the following examples. The first one is going to be that of an elastic collision. So we've got a trolley A of mass 4 kgs, which is going to collide with a stationary trolley of mass 2 kgs. So this is trolley A, and then this is trolley B. The mass of trolley A is 4 kgs, and the mass of trolley B is 2 kgs. B moves to the right with twice the speed of A because it is half the mass of A. So what am I saying there? So I'm going to use a free body diagram. So this one is going to the right with 2 meters per second. And then this one is stationary. Then after the collision, what's going to happen is B will move to the right. So this is B, this is A. So B will move to the right, and A also will move to the right because A has a larger mass. Okay, so that will be the 4 kg one and the 2 kg one over there. So after the, but then B would have to move with twice the speed of A because it is half the mass of A. But the total momentum that is before the collision should equal to total momentum after the collision. So please take note of that. The total momentum is conserved. So we are going to say, so we are told that B is moving to the right, so which means twice the speed. That's now 4 meters per second. And then we can find the speed of A after the collision. So using a diagram like this would make you understand exactly what is going on, so that you don't get confused. So the total momentum before the collision is equal to the mass times the speed of A. So mass of A is 4. Initial speed of A is 2. So that's where you're getting this 4 and the 2 over there. And then the initial momentum of B is 0. That's the mass times its initial velocity is stationary, so it will be 0. And then the total momentum before impact would be 8 kg meters per second. Now the momentum of A and B after the impact is equal to 4 times 0. So we are going to assume that A is going to be stationary after the collision. So A is going to stop, but B is going to move off with the speed, which is 2x. Since momentum is conserved, we are going to say 8, the total momentum before collision, should equal total momentum after collision, which is 2x. So 2x is equal to 8, so which means x would be equal to 4 meters per second. Right, example number 2 is that of an inelastic collision. Now, just to shed more light on elastic collision, the first one. In an elastic collision, apart from having the momentum being conserved, we also have the kinetic energy being conserved. That's the total kinetic energy is also conserved. Okay. However, in an inelastic collision, only the momentum is conserved. So P is conserved, but then kinetic energy is not conserved. So what it means is the kinetic energy before collision is not the same as the kinetic energy after collision. After collision, you're going to have less kinetic energy. Why? Because it has been converted to other forms, e.g. heat, sound during the impact. Now, in this example, trolley A moves to the right with a speed of 2 meters per second, collides with trolley B moving to the left with a speed of 1 meter per second. So trolley A moving to the right with 2 meters per second. Remember, its mass is 4 kgs. And then trolley B is now moving to the left 1 meter per second. So remember, we said momentum is a vector quantity, so which means momentum to the left is going to be negative. So after the collision, we are going to have the trolleys moving in different directions. So I'm going to go with it slowly. So to the right is trolley A, which is 4 times 2, right? So that's positive momentum. And then trolley B is the one now moving to the left, so it will multiply by negative so that it is to the left. So which means the total momentum before collision is going to be 8 minus 2, which is 6 kg meters per second. Right. Now, after the collision, you are told that, what did they say? So as the trolleys stick on impact and move off together after impact. So which means you're going to have the trolleys combining to form one. So the total mass is going to be 6 kgs. and then they're going to move off in the same direction, which is, we are going to assume that is going to move to the right. So if your answer comes out as a negative, it means that what the direction you've assumed is going to be the wrong, is not the correct direction, so it will show you by a negative. So the total momentum after collision is going to be 6x. That's the combined mass times the common velocity. Now to get this common velocity, we are going to equate the two momenta. So it's going to be 6 kg meters per second is equal to 6x, which you're seeing there. So finding x, you divide by 6 both sides, and you get 1 meter per second. So which means both A and B would move off together to the right with a speed of 1 meter per second. Then my third example is that of an explosion. A spring is placed between trolleys A and B, and both trolleys are held stationary. So we've got a spring, and then we've got trolley B, and then we've got trolley A, like this. So they are going to compress the springs, right, and then release. So when we release, A would move this way, B would move that way. So A will move to the left with a speed of x, and B moves to the right with a speed of 2 meters per second. So that's 2 meters per second over there. Diagrams do help to understand what's going on. So the total momentum before collision, so I always want to do this. So before, separating before and after. So the total momentum before collision was 0 because they were stationary, they were not moving, both of them. Then after collision, we are having A moving to the left, so the momentum is going to be negative. So it's going to be negative 4x plus the momentum of B, which is to the right, which is positive. So 2 times 2. So that's what you're seeing over there. So which means minus 4x plus 4 is equal to 0. So making x the subject of the formula would give you positive 1 meter per second. So which means A is going to move off with a speed of 1 meter per second. So which means the direction that we have assumed is the correct one. Now A, having double the mass of B, moves to the left with half the velocity of B in that case. Now the principle of conservation of momentum states that when two or more objects act on each other, that is when they interact, e.g. in a collision, the momentum of the objects before the collision is equal to the momentum of the objects after the collision, provided there are no external forces acting on the system. External forces can be frictional force. I think I should end it here. Please let me know in the comments whether you understood the topic, and please remember also to like, share, as well as to subscribe to the Physics Tips for Cambridge Students YouTube channel. Signing out.